Welcome back, folks. We're looking at current dividers. We're going to look at an example that has more than two components in parallel, and we're going to figure out how to get the individual currents through the branches. With the voltage divider, it was nice and straightforward. We just tacked some terms onto the denominator. With the current divider, we have to remember that we're limited to two parallel branches because of the way that it's derived. So I have a circuit with three parallel branches, and we're going to go find those currents. And that circuit looks like this. Okay, so to find IR2, we can look here, but we're limited to two parallel branches. So we got to figure out what to do with these other branches. Now we're thinking about applying the current divider, so we have to stop and say, am I trying to relate a current to some other current? And we are in this case. We're trying to figure out how this 24 milliamps splits between these three branches. Right now we're going to find IR2, and we have to say, are the branches actually in parallel? Well, I see a node up on top here, and I see a node on the bottom, and all three resistors are connected to those same two nodes. So they're all in parallel. Okay, so what do we do with this? And the answer is we take this circuit and we redraw it and we force it to look like the current divider that we know and love. Okay, so I'm going to redraw this in the form that we used in the last video, and it looks something like this. Okay, now this resistor, I'm going to keep that one as R2. We need to keep that one separate because if I combine it, I'm going to lose track of that current all by itself there. So we're going to leave that as R2, and that's 6K. And this resistor over here becomes the parallel combination of these two. Some people get uncomfortable with this because R2 is in the center of it, but the definition of being electrically in parallel just says that they need to be connected to the same two nodes. We already checked that they're connected to the same two nodes. So even though they're separated by another component going down the middle here, they're still electrically in parallel, and we can say that this is going to be R1 in parallel with R3. Okay, so that's 4K in parallel with 12K, and we should go do that on the calculator. So let's see, 4K, I'm going to invert that. I'm going to add 12K to it, and I'm going to invert that, and then invert the result, and we see that it's 3K. Okay, so that is equal to 3K. Now in this form, we can apply the current divider. So we can say IR2, I'll stick it out here. No, I won't. Not even nearly enough room to do that. Let's stick it down here. IR2 is equal to 24 milliamps. Okay, and then we have our ratios of resistance. If I want to know the current through this branch, I multiply by the opposite branch resistance. So that's 3K in this case. And then I divide by the sum of the branch resistances. Okay, so that looks like it's going to be 3K over 9K, or 1/3, and 1/3 of 24 milliamps is going to be 8 milliamps. Okay, so we can play the same games with the other two currents. We can say, well, IR1 is going to be 24 milliamps. Okay, the opposite branch resistance is going to be the parallel combination of the other two, right? So if I'm finding this current, I want to combine these two in parallel. So this is going to be 6K in parallel with 12K. And I'm going to divide by 6K in parallel with 12K, okay, plus 4K of that branch. Okay. Well, 6K in parallel with 12K is 4K. All right. take out your calculator. Use the tool that you're going to use on exams in your life. If you're going to take the FE, make sure you're using one that you can use on the FE. Practice with the tool that you're going to use. Figure out that 6K in parallel with 12K is 4K. Okay, and we have 4K over 4K plus 4K. So that looks like it's all going to be a half. Half of 24 milliamps is 12 milliamps. All right. Last branch, IR3. That 24 milliamps is going to split again. And it's going to split. Let's figure out what's going on here. It's going to split between the 12K and 6K and 4K in parallel. Okay, so this is going to be 6K and 4K. And is it 12K? Right. Sorry for all the scrolling. And 12K. Okay, so this is a fun one. 6K in parallel with 4K. I believe is 2.4K. I'm going to go check that. I don't trust me today. I don't trust me any day. 6K in parallel with 4K is in fact 2.4K. All right. I hope you believe in me because apparently I don't. So 2.4K over 14.4K. Let's go ahead and just do that here. 2.4K divided by 14.4K, since I add the 12K to the denominator, and I multiply that by 24 milliamps. And I get 4 milliamps. Okay, so 4 milliamps, 12 milliamps, and 8 milliamps. So here's 8. What did I have? I had 12. And we have 4 over here. Now, doing the gut check, the biggest resistance should have the least current, and the smallest resistance should have the most current. Okay, and here's 12K, that's the biggest, and there's 4 mils, that's the smallest. Okay, it's the opposite of the voltage divider. Here's the lowest resistance, and it has the biggest current. So we're in good shape there. Ooh, you can see through my face. My beard's bleeding through the blue screen right now. Can't wait till the green screen comes in. Okay, so that's our current divider. Make sure we're being careful when you have more than 2 branches. Know that you have to stop and force it to look like the 2-branch version by combining a couple of the branches together. Okay, we're going to look at another example in the next video, and then we're going to start building up our third and final fundamental law of circuit analysis. Stay tuned and good luck.